Hello Pre-Calc students, this is Unit 6, Day 1, and this is our introduction to functions. So we're going to start with these two warm-up problems. You should definitely try these problems before watching the answers. So in the first one, an investor assessed the average daily value of a share of a certain stock over a 20-day period. So here you see the 20-day period. The value of the stock is approximated with this function, where D represents the day of the assessment. So the first problem says to use the graph to estimate the value of the stock on the 10th day. So here's the 10th day right here, and we're going to go up to the graph, and then we're going to go across. And it looks like we're somewhere between 30 and 36. So you could guess 31, 32, 33. So let's say $31 per share. But we're going to use the graph. Let's see. Then we're going to confirm your estimate algebraically. So literally, we could plug 10 in for all these D's. So that would be a lot of typing on your calculator. 0.002 times 10 to the 4th minus 0.11 times 10 to the 3rd. You get the idea. So instead of doing that, what we're going to do is we're going to use the calculator. And in the calculator, you can press y equals, and you can put the function in there. So 0.002x to the 4th. The reason this is better is because now I can use the table of values to find all of these other values that I'm going to need later. So I'm going to press now second table, and I want to find the value of the stock on the 10th day. So you can see on the 10th day it was exactly $32. So we're going to write that down. Okay. Algebraically, it was $32. All right. Use the graph to estimate the days during which the stock was valued at $30 a share. So $30 a share is just a little bit lower down here. And it looked like it happened 3 times. Right here, and right here. So we're going to do our best to estimate. That first one looks like day 0. Okay, over here we're between 8 and 10, so I'm going to say day 9. And over here we're going to say that's about day 15. So we're going to look at those days on your calculator and see if in fact it was valued at $30 a share. All right. So day 15 is right here. I can see it was $30.25 a share. And day 9, $29.90 a share. So let's put those in. $29.90 and $30.25. So those are pretty close to the $30. And then the last one was day 0. So you want to go back and check day 0. Day 0 was 31, so that was not as close as the others, but still not too far off, $31 per share. So in confirming algebraically, we're going to just say that we were pretty close. All right, next situation. Bottled water consumption from 1977 to 2006 is modeled with this quadratic function, where x represents the number of years since 1977. So the first question asks to estimate the amount of bottled water in 1994. But if you look at the graph, you'll see 1994 is not on the graph. This is the years since 1977. So if I want to know how many years between 1977 and 1994, I can subtract. 1994 minus 1977, and you should get 17 years. So 17 is going to be a little bit before 18. Go up and go over. It looks like 3,000 million gallons. Think about that number, 3,000 million. What is that? Well, let's see. If I wanted a million, here's my thousands place and my hundreds place. So you put a 3,000 in front of that. And what you really have is 3 billion. 3,000 million is 3 billion, but for some reason they write 3,000 million. I don't know why. So use the graph to estimate the amount of bottled water. So you could write 3,000 million if you want, or you could write 3 billion. 3 billion gallons. All right, let's look at the next one. Find the 1994 consumption algebraically. Round to the nearest million gallons. So we want to put this function into our y equals. Okay, let's move it over so I can see. Y equals, and clear the other one out, 9.35 x squared minus 12.7 x, oops, I forgot my decimal, plus 541.7. Okay. We need to change our window. Well, actually, I don't need to change my window because I don't need to look at the graph. I'm just looking at the table of values. So second table, and I'm trying to find out 17 years, so I need to scroll down. All right. In 17 years, the consumption is 3,028 million. It says to round to the nearest 10 million gallons. So you could write 3.028 billion, but because they're asking you to round to the nearest 10 million gallons, that means to round to this tens place right here. The number after the 2 is an 8, that rounds that 2 up. So your number is going to be 3,030. Let's see, where's my pen? Okay. So 3,030 million gallons. And the last one says to use the graph to estimate when the water consumption was 6 billion gallons. So 6 billion is 6,000 million over here. Looks like we're a little bit past that line. So going straight down, I would estimate about 25 years. 25 years after 1977 is the year 2002. And to confirm that algebraically, I'm going to look at 25 years on the calculator. So after 25 years, it looks like 6,068 million gallons. So 6.068 billion. 6.068 billion, so that's pretty close. It's a good estimate we made. All right, so next we need to talk about some special functions. We have rational functions and we have square root functions. So let's look at the rational functions. And let's see, I have a highlighter. So you may want to highlight rational functions and square root functions. These are the little subtitles here. Okay. If you have a rational function, and rational comes from the word ratio, so it's a fraction, it's a ratio, any value that makes the denominator 0 has to be left out because your denominator can't be 0. Division by 0 is undefined. So let's look at this example before we move on to the square roots. The denominator can't equal 0, so the procedure is to set the denominator not equal to 0. So I'm going to write x squared minus 4 cannot equal 0. Add 4 to both sides, get x squared cannot equal 4. And when you solve with a square root, don't forget your plus or minus. So x cannot equal positive 2 or negative 2. And remember, we didn't solve anything, we just found the values that x cannot equal. So we found the domain. All right, in the next one, we have square root functions. Any radical with an even index, so a square root, a fourth root, a sixth root, and any value that makes the radicand negative must be left out. Because if I have the square root or the fourth root of a negative number, well, that's not real. That's an imaginary number, and I can't graph an imaginary number. So the procedure to find the domain is to set the radicand, that's this part right here, greater than or equal to 0. So 2x minus 1 has to be greater than or equal to 0. And x is greater than or equal to 1/2. So sometimes you'll see the domain written this way, or sometimes you'll see it written in interval notation, 1/2 to infinity. So one or the other. All right, and this last one is a cube root. And notice, because the index is odd, we don't need to follow this rule. You can actually take the cube root of a negative number. Think about the cube root of -8. The cube root of -8 is -2. So these have solutions, these work. So because you can take the cube root of any kind of number, then this function has no restrictions. But that's not the domain. The domain is -infinity to infinity. All right, turn the page. We're going to do just the top part of the next page. These are your practice problems, so you should pause the video before you move on and check and see if you did them correct. So first one we have is a square root. For the square root, you need the inside to be positive, so you write x minus 4 is greater than or equal to 0, which gives you x is greater than or equal to 4. And you can leave it like that, or you can say that the domain starts at 4 and goes to infinity. All right, next one's a rational function, and we need to say that the denominator cannot equal 0. You want to factor this, and it looks like both terms have a common factor of x, so take the x out and set each factor equal to 0, or in this case, unequal to 0. So x can't equal 0 and x can't equal 4, and that's my domain. All right, the next one. There's no square root on this. There's no fraction, so there's no denominator. Looking carefully at this, I recognize this as a quadratic function, which is the shape of a parabola. So if you have a parabola, the left side is going to be going to -infinity, and the right side is going to be going to positive infinity. So your domain is -infinity to positive infinity. All right, and here we have another square root. So we're going to set the inside part, 5 minus 3x, greater than or equal to 0. -3x is greater than or equal to -5. And when you divide by -3, remember to flip your inequality. So x is less than or equal to 5/3. So you can write your domain this way, or you can write -infinity to 5/3. Okay, so that's the end of your first video. You can stop this and start your next video.